All right, let's go ahead and talk through some of the information necessary to complete this next lab. So we've got kinetic and potential energy that we're going to talk about today. As before, you start with a good introduction screen, plenty of formulas and general information you can use to get started. Some of it should look familiar. So we can find average velocity by taking displacement divided by change in time, which we can find based off of the data points from the moving objects. Then, because we're going to have velocities in multiple directions, it's going to move horizontally in x and vertically in y. Then to find an overall velocity, we're going to basically do Pythagorean theorem with those numbers. Then we have a couple of formulas that you will have noticed from either from the book or from lecture. If you've taken that, we've got potential energy that we're going to look at first, and then kinetic energy that's going to change very slightly because the ball is rolling as it's moving. So we're going to see how that changes things in a little bit. Going over these formulas and the provided information, if you go to lab data and these little tags, links here, bring up these different formulas. Your gravitational potential energy, so U for potential energy and a little g to show that it's gravitational, comes from mass times gravity times height, where height is the relative amount that it can fall. Basically, how much does it drop down or raise up in the y direction, and that's going to change how the potential works. Okay, and you do want to make sure that your mass is in kilograms as it is here, gravity is in standard units, and then we want to make sure we're using meters so that these units combine properly to make joules. Average velocity, as we talked about earlier, is similar to what we've seen before. So your change in position over change in time, you can do that for x and y. And so your overall velocity is going to come from essentially doing Pythagorean theorem with those. Um, Depending on what information you're starting with, and this is a trick we're going to use later, rather than doing Pythagorean theorem with these velocities, if you do that with your position vector first, so take your displacements and do Pythagorean theorem with those, then you can use that directly to find your average velocity. Then speed, as mentioned, it's one of the options, one of the ways that we can combine from here. You've got multiple ways you can get these answers. Can come from taking the x velocity, the y velocity, doing Pythagorean theorem, and combining them. Kinetic energy is on its own for just generic moving objects, 1/2 mass times velocity squared. When things are rolling, though, we have this moment of inertia formula that pops up. So 1/2 I omega squared. So I is the moment of inertia, omega is the rotational velocity. And so we need to convert with these. Thankfully, some of the information is consistent between these and can cancel. So in the book, the I, the moment of inertia for a sphere, is 2/5 mr squared. And that r squared is important because omega can be rearranged. Velocity is equal to r times omega. And so if we take that, solve for omega, then it's going to be v velocity divided by r. And because that gets squared, excuse me, then the r squared factors actually cancel out. And then thankfully, if that's gone, then what we have is this v here that gets squared, and then that's in common between the v squared that's here and v squared we end up with there, and this can be factored and combined. So basically, they give us a slightly altered version of the kinetic energy formula that we can use because it's a rolling ball and not just some sliding or flying object. All right, and then last big formula we need for here, your total mechanical energy is just the combination of kinetic energy and potential energy added together. We have conservation of energy, so we're not going to lose or gain energies, we're just going to switch between types. So if there's a lower kinetic energy, it's because some of that kinetic went to potential. If there's a lower potential energy, it's because some of that went to kinetic, and so on. But your total energy, in theory, should stay constant. All right, so this lab starts out the way most of them do. So they give us a video. These balls are going to move along the path. You can see that there's one in the foreground and one in the background. They move with each other for a moment, and then there's sort of a break in the path here where one drops to a lower level and then eventually comes back up. So that may have an interesting effect on the total movement of the ball across the path. So you may have in mind, okay, well, maybe this one's moving along the longer path because it drops down and comes back again. Or you might think, okay, well, it's going along the same distance this way. We'll see. So it does ask you to make a guess at the beginning. If you guess incorrectly, then it gives you a hint. So I'm not going to give you any more information here because you can just try it based off of your own knowledge, and then you can make an adjustment if it doesn't end up working the way you think. All right, then again, hopefully this doesn't spoil anything, but the video after the balls are already at the end. Then once you've watched the video, then there's a button to click to continue, and then it follows up with some more questions. Again, no hints given here because if you get it wrong, it'll give you hints for picking a new answer. All right, then after that, it finishes phase 1. Then phase 2, like we've seen in the other labs, we want to find our conversion numbers, and then we want to do our first set of calculations. Then, as with other labs, the further calculations will be done automatically as you track the ball across the path. Okay, so the ball moves down the track a little bit here. They were released at, I guess, very slightly different times, or we're at a little bit of an awkward angle here, because in theory they should have been rolling next to each other here. But we're going to calculate based off of just the one ball, so hopefully the information stays a little more consistent. So one frame, we need to find out how much time that's going to be on its own, and so we do need to read very carefully. The video is recorded at 29.94 frames per second. So this changes between different labs and possibly changes slightly between different students. So you may see 29.97 or 30, or on other labs you may see 15 frames or 60 frames. But to get this answer, if there are 29.94 frames per 1 second, and we want to know how many seconds are per one frame, we're turning that back the other way, then you would have 1 divided by 29.94. And then technically what this is telling you now, this is 1 second for 29.94 frames. And so that's end up giving you a conversion for seconds per frame. Then similarly, you need a conversion for distance. So the total track is 1.5 meters. And then it's going to give you a number of pixels. So I'm not showing you what that is here because I know for sure that changes between different students, and I don't want to give some students answers and not others. So you can see what my answer was, but you can't see what my pixels were. So, if this is 1,000, 2,000, 3,000, or if it's 55, whatever your number of pixels will be divided under here to give you your conversion. So technically this is 0.00117 meters per pixel. Then we can use that because the minimum Y position, whatever your number was there, and I think I accidentally showed it on the last one, right? So 105. Then what you would do is you would take 105 pixels and stick that over 1, and then multiply that by our conversion that we just found, that there's 0.00117 meters per pixel. So technically pixel units cancel each other. These two things are going to multiply and it's going to give you an answer here. Okay, so you do want to be very careful to round to the appropriate places. So it tells you number of decimal places here. Unfortunately, a couple of these are off a little bit, where it'll say it wants 5 decimal places, but it really takes 4, or sometimes demands 4. And that's just something that you'll have to watch out for as you're working through the lab. So if it ever tells you an answer is wrong, round a place shorter or add an extra decimal place, or round the number up or down very slightly, and a lot of times that's what they're looking for. So unfortunately these do round a little funny sometimes. As a reference though, we need to know that The timing starts on frame 4. So they actually let the ball roll for a little bit before they start counting frames and picking different spots here. So that's going to be important as we're plugging in values, because at the beginning, when our first reference point is frame 7, then we want to keep in mind that frame 7 is only actually 3 seconds after when this was 0. So technically, there's just a little mark here, but this should be 0 seconds. And so our elapsed time here, where this number right here comes from, is 7 minus 4 is 3. So, sorry, 3 frames. And then that's going to multiply by our conversion, where 1 frame is 0.0334 seconds. Okay, and so then multiplying these together will give us our time right there. Then we have pixels listed here. So 48 pixels is our given value, then 143 pixels is our given value for the Y part. And we multiply those by our pixel to meter conversion, and that's where these other values come from. Now, remember, excuse me, that the U is mass times gravity times height, where the height is the change in the Y position. So here, this would be the mass as 0.085 kilograms, Earth gravity 9.8 meters per second squared, and then the change in height is the difference between these Y positions. So in here, I'm going to stack them to save a little bit of space, but then you would have the difference in these. So you'll have 0.1697 minus 0.1673, and then these are in meters, and then all combined kilograms times meters squared when these combine, and seconds squared makes joules, and that's where this number is going to come from. All right, then your x velocity, again, that's your change in x position. So delta x over delta t. You change in x position, you're looking at the numbers on this side this time. So you'll have 0.0562 minus 0.0480. And that's going to be divided by your change in time, which is technically here 0.1002 minus 0, because remember they took 4 frames to be the 0 second mark. You will do a similar conversion, which I will not show, to find your Y velocity, then Pythagorean theorem with those numbers to get your overall velocity. Be careful with this negative sign. So because it's dropping down in Y, this does turn negative on this part. When you square it, it should turn positive. Now, one more little minor error. Technically, you can plug in a calculator and you can get a value here, but it ends up being so close to 0 that this software rounds to 0. So even though it's moving and it should have some kinetic energy, it's not actually high enough to count in the software. You can also see that's why our total energy technically drops a little when it shouldn't. All right, then from here, again, we get additional data points, and the software will automatically run through and calculate those. So we click a bunch of times. It gives more example calculations in case you had trouble with it before. And you're only tracking the ball on the back path, but then that's going to give you all of this automatically generated information here. Okay, then a couple of calculations that we need to make. So it says to calculate the average velocity. So average velocity is going to be your total distance traveled divided by time. So make sure you're looking at time in the correct column and not looking at frames. And then also make sure you're looking at your total distance. So technically, you should find your change from your original x position and your final x position and your original y position and your final y position and do Pythagorean theorem with these. But as it turns out, there's such a little change in y that even if you do your full calculation, it only changes the answer by about 2/3 of a millimeter. So it's approximately equivalent to just use x. So not technically quite correct, but it does work out well enough here. So if we were to do this calculation, we'd have 1.422 for our final x position minus the original 0.0480, then divided by the time. Well, because the time started on technically 0 seconds, then really it's just the time here at the end, 2.1042. And that's going to give you the 0.65 that I've got. Let's round it down slightly, but again, it rounds to the same number even if you do the other part of the calculation. Then for the extra part here, you do have to be careful because it gives you a time, and this may change between students. So you would do the same type of calculation, but because the ball passes through the end faster, then you would end up dividing by a different time at the bottom. And because it's a smaller time, then you end up getting a bigger answer, and that's why we see that the other one is a little faster. Okay, then from here, we want to throw all of this information into a graph. This is going to use your automatically tabulated information from earlier. You just have to tell it in what order and what way to use it. As we've talked about before, typically for your horizontal axis, it's pretty much always going to be time. And then your vertical axis is going to change depending on what you're looking for. So here it's energy versus time. So then we want to make sure we're picking the one that says energy and not position or velocity. Then the graph type, typically we want a scatter plot so that it takes our different data points, throws them on a graph, and then we will create the graph, show regression, and then save so that it will be recorded. Couple of check your concept questions. Again, no hints with these because it should tell you. So, give it your best shot. Think about it though. Kinetic energy deals with motion. So I guess I lied, small hint here. But it wasn't moving at first and then it starts moving. And then think about if it's going faster or slower as it's moving down the track. In a similar way, gravitational energy is based off of height. So the higher up it is, versus the lower down it is, it's going to change the potential. Think about what that's going to look like. And I've already spoiled this from earlier. In theory, your total energy should be pretty much the same throughout. All right, so here's a version of our graph. Unfortunately, I've noticed that this happens in a couple of examples, but occasionally there are some broken data points that go towards the front. And that's from the beginning where technically we should have had a data point here and here for 0 time. And occasionally these don't track properly and they end up sort of off the graph, like almost as if they're negative numbers. And that does unfortunately break the regression line. So there's supposed to be a line sort of tracking through these roughly like this, and then another one that should go roughly like that. And then this one should be something like here. But they don't work with these data points that are off the side. So unfortunately, not an applicable number in AN. We don't get numbers for those. But normally there should be something. If that happens to you, then when you get to your data points here, you're not going to have anything to put. If it worked, then you'd have a number that would put here. But if you end up with NAN, which seems to happen about half the time from what I can see, then you're going to have to put 0 because that part of the graph was broken. Okay, so unfortunately, there's really just not anything to do with that. Then at the end, we're supposed to look at the final energy here, and then we're supposed to end up with the difference in energy for the last part. But because this is 0, because the graph was broken, then technically we have this number minus 0, which obviously puts the same number back in again. If your graph is working, then you will have actual values here and you will subtract that value. All right, and then that's it. So as long as you went through and you answered everything, you get a congratulation page. If you didn't, if you submitted early or if you ran out of time, then you'll get a percentage for whatever you completed.